Hello, everyone. My name is Bryce Adelstein Lelbach, and I'm going to talk to you today about the C++20 synchronization library. I am the CppCon program chair, and I work at NVIDIA, where I lead the CUDA C++ core libraries team. I'm also a member and officer of the C++ Standards Committee. I chair the Library Evolution Incubator Group and the Tooling Study Group. But originally, when I first came to the committee, I served on the concurrency study group. So that's why I'm here talking to you today about concurrency and synchronization. So first, I want to talk about something that I think is more important. I think before you can solve a problem, you have to recognize that you have one. And as a leader in the C++ community, I want to publicly acknowledge that C++ has a diversity problem. We have a great group. It's called Include C++, it's this great group of people who are really committed to solving this problem. If you're interested in learning more about diversity in C++ and what you can do to help, go to includecpp.org and join our Discord server. All right. So C++20 synchronization library. Some of you may be wondering, well, don't we already have a bunch of synchronization primitives in C++? They were added in C++11 when we added threading support and a memory model to the language. And we have things like mutex and condition variables. Like, isn't that good enough? Well, all of those things were designed a decade ago at the dawn of the multi-core era. Today, almost all processors are parallel. And we frequently deal with hundreds to hundreds of thousands of threads, sometimes even more than that. And so we need a new set of synchronization primitives that are better designed for this new era of massively parallel hardware. So C++20 introduces some new scalable synchronization primitives and some other enhancements to the standard library. So I try to use as much C++20 in this talk as possible, including ranges. Most of the range facilities are in these two embedded nested namespaces, std : ranges and std : views. So I'm just going to use these two namespace aliases so that everything fits on my slides. And so when I was thinking about how to make this talk, originally, I was just going to go through each feature and just explain, like, here's the feature, here's how it works, here's a little example. But then I thought I can actually make one big example and use every feature in that example and just sort of tell one continuous story throughout the entire talk. So I'm going to attempt to do that. And the example I'm going to build for you is a little tasking runtime. Before I worked at NVIDIA, I worked on an open source parallel runtime called HPX. So this is sort of going back to my roots. So there's four key elements that we need for a tasking runtime. First of all, we need some set of worker threads that are going to actually execute the task. So we need some execution resources that are going to actually run the work. Then we need some sort of queue where we're going to put the work in, and then the worker threads will take work out of that queue and execute it. Then we need some sort of termination detection mechanism. This seems like it might be like a little detail or an afterthought or something that's, doesn't really belong on the list of major features of this tasking runtime, but it's actually pretty tricky to get this part right. And then we're going to build some facilities on top of our little tasking runtime, some parallel algorithms. All right, so we're going to start off by figuring out how we're going to organize our pool of worker threads. So as I mentioned in C++11, we have std thread, which is a low-level abstraction for creating threads. So if we need like a bunch of threads, we can create something like this. So this is just some thread group class. It's got a vector of std threads. And in the constructor of this thread group class, I give it a count of how many threads I want. And then I give it one invocable. So just an invocable is a C++20 concept for some object that can be called. So a function object, et cetera. And then I create one std thread for each of the count that I specified here. So this is pretty straightforward. But even this straightforward code has a bug in it. And the bug is that when you destroy a std thread that has not been joined, std terminate is called. So if we go and we create our thread group class right here, we say we want 6 threads. We're going to give it a function that just increments this atomic count right here. So what's going to happen is when this thread group object goes out of scope at the end of this block scope right here, it's going to be destroyed, and it's going to destroy all of these std threads. And we haven't joined with those std threads, so std terminate will get called. This is sort of unintuitive. Usually in C++, we expect things to act with ray semantics. So they acquire their resources on creation, so the thread gets created when you construct the std thread object. And you would expect that when you destroy a std thread object that it cleans itself up nicely. Std thread, unfortunately, doesn't do that. So we can go and add a destructor to our thread group class like this that just calls thread.join on each one of the std threads. And that's fine. But we have to remember to do this. And remembering to do this is kind of annoying. So we're planning on using our thread group to implement a task pool, as I mentioned. That means that each worker thread is going to be executing some loop that processes work continuously. So we'll use this little dumb function as a sort of little placeholder for what the thread function will look like, where we're just going to be in some loop that's going to be like while true or while some termination condition, and then we're going to execute work. In this case, we don't have any work yet, so we're just going to increment this atomic. But we have to come up with some way to figure out when the workers are done. How do we signal to them that they need to exit this loop? So we have to build some sort of side channel for that if we're using std thread. We could use atomics to do this. So I've created some std atomic bool here that starts off initialized to false. And then inside of the worker thread function, instead of just while true, they do while the atomic is not, while the atomic has not been set, we're going to keep incrementing this other atomic. And then at the end here, to actually signal to all those threads that I created that I want them to be done, I just store to this done variable right here. So again, you can do this. This is somewhat straightforward, but you have to remember to do this. And if you don't, you might end up deadlocking here because your threads might just end up in their loop forever, never receiving their signal. So in C++ 20, we have std jthread. The J stands for joining, although it is also the first letter of the last name of the author who proposed this feature. So you can think of it in sort of either way, either being std jasudas thread or std joining thread. And jthread joins in its destructor. So it does not have that problem that std thread has, where we have to remember to add a destructor to our thread group class to explicitly join with each one of those thread objects. And std jthread also has some other enhancements. So it's just like std thread, except if the thread is joinable, it joins with it instead of calling terminate in the destructor. And it also has a nifty interruption mechanism, which you can use to signal to a std jthread that you would like it to stop doing whatever it's doing. So we can do that by instead of the thread functions for jthreads, they can take either a just regular invocable that takes no arguments, or they can take an invocable that takes a stop token. And a stop token is a thing that you can query and ask, hey, have I received a stop request yet? And then you can, once you've received the stop request, you can do whatever you want with that. Presumably, you want to honor that request and exit, but threads, it's optional. You don't have to respect it. And then you can also request that a thread stops. So I've added this request stop member here that just iterates through all the members of this vector and calls request stop on them, which will then set the stop token that's been passed into each one of their worker thread functions. It will signal to that stop token that a request has been stopped, that stop request has been sent. So std JThread supports interruption. Std thread takes an invocable that takes no parameters. Std JThread can take an invocable that either takes no parameters or that takes a stop token parameter. And you can, there's a couple different parts of this stop token machinery. So you've got stop source, which is sort of analogous to a promise. It is the producer of stop requests. It owns the shared state of the stop request. Then you've got a stop token, which is a handle to a stop source. It's the consumer. It can only query whether or not a stop request has been made. It can't make a stop request. This is the consumer side that the worker thread receives. And then there's a callback mechanism called stop callback, which you can use to, it's sort of analogous to future then. You can use it to register invocables that you want to be run when you've received a stop request. And then on std JThread, you can query, you can get the stop source associated with the JThread. You can get a stop token associated with the JThread. And then, as I showed, you can request that a JThread stop. So this is a useful mechanism because it means that you no longer have to build your own interruption or termination mechanisms. There's also some support in the standard library synchronization primitives for stop token. Unfortunately, not in some of the new facilities that I'm going to show you today, but hopefully in C++ 23, we will fix that little oversight. So condition variable any actually, has a few different polling APIs, and we've added some new ones that support stop tokens. So the way that these work, like this first one right here, this wait until, where I give it a lock, a predicate, that's all normal and what we're used to. And then we give it a stop token. What this does is it will wait for the predicate to be satisfied until, but it will exit early if a stop request has been made. This is quite useful because usually with these hand-rolled interruption mechanisms like the std atomic one that I showed you before, you have to actively poll on the thing. With this interface, you can just tell the underlying system API, hey, I want to wait until until this condition happens or until I receive an interruption request, and your platform can do something more optimal than just polling if it has that option available to it. All right, so now we're going to replace our atomic variable that we were using for signaling termination with a stop token here. So we just changed the thread function to take a stop token, and then in the body of our thread function, we just do while we've not received a stop request, we go and do whatever stuff we're supposed to be doing. Okay, next let's build ourselves the work queue. And again, this work queue is going to be filled with tasks, and each one of the worker threads will continuously pop items out of this queue and execute those items. So we are going to build a concurrent bounded queue. So by bounded, I mean this queue has at most queue depth objects in it at any time. The alternative design is an unbounded queue where it can have any number of objects in it. The trade-off is with a bounded queue, you have a fixed memory footprint. But you potentially have to block if the queue is full. Whereas with an unbounded queue, you never have to block to insert into the queue. But the memory footprint of the queue will just grow until you run out of memory. If you're submitting way more work than you're processing, the queue will grow very quickly. So the reason that we're using a bounded queue in this demo is not because of a conscious choice of me feeling that it's better. It's just because this is the canonical example of how you use semaphores, which is what we're going to talk about next. So this concurrent bounded queue, it's got a std queue of items. Pretty straightforward. Then it's got a std mutex that protects access to the items because we have multiple different threads that are going to be pushing and popping items out of this queue. Then we have two counting semaphores. And counting semaphores are sort of like a generalization of a mutex. A mutex controls access to a single to an entity, and it allows at most one thing to have access to that entity at a time. A counting semaphore allows up to n things to have access to a resource at a time. So it allows us to manage a shared count. So we've got two different counting semaphores here. We've got one that's called items produced. This is going to keep track of how many items are in the queue. And then we've got remaining space. And remaining space is going to keep track of how many entries are left in the queue. How many more things can we insert until the queue is full? So items produced will start off at 0 because the queue starts out as empty. And remaining space will start off at queue depth because initially we can insert up to queue depth items into it. All right, so the queue has an enqueue method, a dequeue method, and then a try dequeue method. We're going to just walk through how those work. OK, first I'm going to talk a little bit about counting semaphore. So counting semaphore looks like this. It has a release method that lets you add some count to it. So if I release 5, that adds 5 to the count of the semaphore. And then it's got some acquire methods which take one count from the semaphore. So we've got our typical blocking acquire. Then we have a try version that polls. Then we have a try version that polls with a timeout and both a relative and an absolute timeout. This is somewhat similar to wait APIs on condition variable and various try lock APIs on mutex. The counting semaphore, you tell it at compile time as a template parameter what the maximum possible value is that you might want to instantiate this with. This allows implementations to pick optimal implementation strategies. For example, you might have an OS primitive to implement counting semaphore if you know that the count will never exceed 32 bits. But if you need a 64-bit count, you might not be able to use that operating system primitive. You might have to use some other slower mechanism. All right, so that's counting semaphore. First, let's look at this little pop helper function that we have. It's pretty straightforward. So all that this does is it acquires a lock on the items mutex, and then it pops an item out of the stood queue. The only reason that it looks a little bit complicated is because the pop interface on stood queue is a little bit unfortunate in that it doesn't actually return the item that it pops out. So first you have to get the item, which we do here by doing a stood move on the item at the front of the queue. Then we pop it, which takes the empty item out, and then we return the thing that we popped out. So yeah, so just explain. OK, then let's look at our enqueue method. So our enqueue method, we take some value that we want to put into the queue. The first thing we do, we have to make sure that we've got space in the queue for it. So we attempt to acquire on the remaining space semaphore. And if the remaining space semaphore has no count, then this call will block until somebody releases some count to remaining space. Then we go ahead and lock the item's mutex, and we insert the item into the queue. Now, you might notice here we're using both a mutex and a semaphore. That's because the semaphore alone does not protect access to the queue. For example, if we have 8 remaining space in the queue, 8 different threads might at the same time concurrently be calling in queue and concurrently acquire the count there. So those guys all have gotten a count. They know that there's space in the queue for them to insert their item. But we still need the mutex to ensure that they don't try to add the item to the mutex to the queue at the same exact time. So then after we've added the item to the queue, we want to go and let anybody who's waiting to dequeue an item know that we've added a new item. And we do that by releasing a count of 1 to the items produced semaphore. So now let's take a look at DQ, and DQ is pretty much just the inverse of what we just saw. So in DQ, we go and attempt to acquire a count from the items produced semaphore. And then once we've done that successfully, we pop a element from the queue. And remember, the pop function we looked at before does the locking for us. And then now that we've taken an item out of the queue, we know that there's we've just freed up space in the queue, so we can release a count to the remaining space, letting anybody who's trying to enqueue know, hey, there's an entry that you can use. And then we return the thing that we popped out. Try DQ is basically the same thing. The only difference is instead of doing a blocking acquire here, we do a try acquire. And if the try acquire fails, we just return an empty optional here. This try DQ returns a stood optional instead of just a T. And if it succeeds, then we just do the same thing as before. We just pop it, and then we release to the remaining space semaphore. And this one is useful because it's a non-blocking API. OK, so this is what our concurrent bounded queue looks like. So let's talk a little bit more about this stood mutex. So stood mutex is a little bit of an unfortunate choice for us to use here, especially for something like a task queue, because stood mutex is fairly heavyweight. On most platforms, stood mutex will use some sort of operating system mutex implementation, which means that calling it might involve a kernel call. It might sleep your thread. It's potentially quite expensive. Now, some implementations will have a fast path where they'll use atomics to try to ensure that if the thing is not contended, that they won't have to actually make an operating system call. But this is almost always going to be an OS primitive, and it's going to be fairly heavyweight. So it would be nice if we can use something that's a little bit lighter weight, that'll have lower latency, and it won't have as much overhead. So one alternative is that we could build a spin mutex that just uses a stood atomic. So here we've got a stood atomic bool, and the implementation of our lock function is just going to be a while loop that constantly tries to exchange true to this flag. And if it succeeds, then it has acquired the lock. And then the unlock function is just going to store false to the flag. And that's pretty much it. Now, we could also use atomic flag to implement this. Instead of exchange, we'd use test and set here. And instead of storing a value of false, we'd use clear. Now, the issue with this is while this is very low latency, it is not very resource efficient, because we have this while loop right here where we're just constantly spinning and pounding on this atomic. So if a large number of threads are all trying to acquire this mutex at the same time, this isn't going to perform very well, because all of those threads are just going to be constantly hammering away trying to acquire this atomic. So this does not perform well under contention at all. So there's some alternatives to this design. You can add some back-off mechanisms. So instead of just constantly spinning on this atomic, you can spin for a little while, and then if you haven't acquired it, you say, well, that probably means that somebody else is trying to acquire it, so we should probably just sleep for a little while. Just go do something else. We're not acquiring this lock, and us attempting to continue to acquire it is just adding to the contention and making life more difficult for everybody else. It's sort of like if you go to a bathroom and there's a really long line at the bathroom, and you just look at the line and you're like, you know what, I'm just going to come back later. I don't want to wait in this line. It's going to clear up, and then at some point in the future, there will be less of a line in the bathroom. So this is what a very platform-specific implementation of such a back-off mechanism might look like. This is actually taken from the Linux x86 back end of HPX's spin mutex. So here's what we do. We've replaced our while loop that just spins on the atomic with this for loop here. And it still does every iteration. It checks this atomic. It attempts to set true to this atomic. But we keep track of how many iterations we've been trying. That's this k variable here. And for the first 4 attempts, we just do nothing. We just make the first 4 attempts with no back-off mechanism. So that's this right here. And then after the first 16 attempts, we do some sort of processor level pause here. So this rep no op sequence is how you sort of do a very short term pause on an x86 processor. And when we've done 64 iterations of this loop, then we start yielding to the operating system by calling schedule yield, which on Linux is the way that you tell the kernel, hey, like this thread, like don't schedule it for a while. Go run some other thread. Like defer me for a little while. And then finally, if we've been spending more than 64 iterations, we just go and call nanosleep for 1,000 nanoseconds. So we actually put our thread to sleep. We're just like, we'll come back in a while, and we'll check to see whether we can acquire this thing. So this is a pretty good implementation. But as you can see here, there's a bunch of magic numbers. Like, how did we pick those numbers of 4, 16, and 64? They were just numbers I made up in like 2013. How did we choose these 3 back-off mechanisms? That's just what seemed to make sense. And of course, it's very platform specific. So this is not something that's like easy for you to put into your code base, even though this is a pretty good mutex alternative. It's pretty good under contention, and it's very low latency. So in C++20, you don't have to write this yourself, because in C++20, we have a wait and notify API that's been added to atomics. And your C++ standard library implementer, they will go off and write whatever nonsense makes sense for your platform, because they're the right people to be doing this anyways, not you. And you just get to leverage that. So the interface looks a bit like this. We've gone back to just having a while loop where we just constantly try to set this flag. But then in the body of the while loop, we do this flag.wait. And what flag.wait says, flag wait true and then some memory order. What this says is, all right, wait until this value has changed from being true to being something else. So the first parameter of wait is the value that you're waiting for it to change to be something different than that value. And so what this will do is, like, if the flag is set, then it would wait until the flag is no longer set. And we'll know that because somebody will notify us when the value's changed. And then we would wake up and we would continue attempting to set it. So this wait call here replaces that whole back-off mechanism we saw on the last slide. How it's actually implemented, it might be implemented in that way. We'll talk a little bit more about the implementation options in a minute. And then on the unlock side, where previously we just cleared the flag, after we've cleared the flag, we now need to call this notify API. And what notify says, there's both notify one and notify all, is it says, hey, go wake up some of the people that are waiting. So in this case, it says, go wake up one person that's waiting and let them know the value's changed. And notify all will say, go wake up everybody that's waiting and let them know that the value's changed. And this is the version with atomic bool, because this is not just an API on atomic flag. This is also an API on just regular std atomic. So here's what std atomic and std atomic flags wait and notify look like. It's just this new wait API. So as I said, it takes a value of what value you're waiting. You're waiting until the value changes from that. And then you've got the notify one and the notify all API. And so there's a couple different ways that this might be implemented on your platform. So you might implement it with a mutex, an operating system mutex. This will work for certain size objects on Linux and Windows. You might use condition variables, OS condition variables. This will work for certain size objects on Linux and Mac. Now, using mutexes or condition variables actually isn't that efficient if you just use them naively, because as mentioned before, OS primitives like mutexes, condition variables, and mutexes tend to have pretty high overheads. So one thing you can do to amortize those overheads is you can have a contention table where you've got a static table of a bunch of mutexes and condition variables. You can use this to basically to optimize the cost of mutex notifies and the cost of holding these CVs. You might not use an OS primitive at all. You might use timed backoff, like the example I showed you before of the handwritten version that I had. And that'll work pretty much everywhere. And you could also just implement it naively as just a spin lock, like the first example we saw, and that'll work everywhere too. The performance will, of course, be terrible. One other little atomic enhancement in C++20 is that we finally added a test method to atomic flag. Previously, there was no way to test if an atomic flag was set without also setting it. There was just test and set before. So I don't use that anywhere. It's just a good thing to know. All right. So this is the final version of our spin mutex, but this still sort of has a bug. And the bug is that this is not a fair mutual exclusion mechanism. What I mean by fair is, let's say we've got two threads, thread A and thread B, and thread A starts attempting to lock this spin mutex. It is possible that some other thread, thread B, could come in, and it just happens to win. It just happens to acquire the atomic before thread A. And it could acquire the atomic and then go and do its thing and then unlock it. But this is unfair because thread A started trying to lock this thing before thread B. Like thread B came and cut in line. And that's not particularly fair. Yeah, this is an unfair mechanism. It's good under contention, but it's not fair. And if we care about fair tech, and we might care about fairness. So there's another type of mutex called a ticket mutex, which is a fair mechanism. So ticket mutex, we've got two counts. We're just going to represent them as stood atomics here. We're going to call them in and out. And so inside of lock on a ticket mutex, the first thing we do is we go and get a number. So we go to the in atomic, we add 1 to it, and we get some count. And that number is our ticket. And then we go into a while loop. And in that while loop, we keep loading out, and we keep checking whether out has been set to whatever our ticket number is. And when out has been set to our ticket number, then we know that we've acquired the lock. And if out hasn't been set to our ticket number, then we wait for out to change before we go and check out again. And again, we're using the wait API here. So we know what value we just loaded. That's the now value. And so we say, hey, out, like this is the value that we just saw from you. Let us know when you've changed from that value. Then in the unlock side, all that we do is we increment the out count by 1. And then we notify anybody who was waiting here. So you can think of this like a ticketing system at a deli counter. You've got some distributor of tickets. That's the in atomic there. If you want to go and order some meat at the deli counter, you go and take a ticket. You get a number. And then there's some sign that says what number is currently being served. And when that sign matches up with the ticket that you got, then you can go and get service. That's how a ticket mutex works. There's one more thing that we can improve here. We don't want these two atomics to live on the same cache line, because that would sort of defeat the whole purpose. We don't want these two we don't want attempts to increment the in atomic to conflict with people who are polling on the out atomic. Because we might have a bunch of people that are polling on that out atomic, and we want it to be very quick for us to go and get a count from the in atomic, because there's no reason for it to not be quick. So what we can do is we can align these atomics to a suitable size so that we know that they won't end up on the same cache line. And there's a C++17 feature that makes it easy for us to do this. It unfortunately has quite a long name, which is stood hardware destructive interference size. There's also stood hardware constructive interference size, which I'm not going to bother explaining right now. So we can just align as stood hardware destructive interference size, and that will ensure that that's some size that your platform has picked that is large enough to ensure that these things will be on different cache lines. All right, so going back to our concurrent bounded queue, that whole little tangent was just so that we could replace stood mutex in our concurrent bounded queue with ticket mutex, which is a lower latency mutex that performs well under contention and is also fair. All right, now let's go and talk about the termination detection mechanism that we need for our little task manager. And we're going to actually build the little task manager now. So we're going to call this thing bounded depth task manager. It's got a concurrent bounded queue. The item type is this any invocable thing. Just pretend that this is a stood function. Stood function doesn't support move-only function objects. And I like all of my slides to be move-only friendly. So any invocable is a thing that was supposed to go into C++20, but missed the train. It was actually also supposed to go into C++17 and C++14. We keep deprioritizing it. A little unfortunate. But it's just a std function that works well with move-only function objects. So that's what this tasks member is. And then we've got a collection of threads using our little thread group thingy from before. We've got our thread function is this process tasks function here. It just looks like this. This is what each one of the threads in that thread group is going to run. So all it is just a while loop that while we've not received a stop request, we're going to dequeue tasks from the queue, and then we're going to execute them. That's the first set of parens here is for the dequeue. And then the second set, because whatever we've returned here is an invocable, the second set is executing that task. So it's pretty straightforward. And then this is just the constructor, which just passes a lambda that calls the process tasks function. All right, so now let's look at how we give work to this task manager. We have this submit method. It takes an invocable, so a function object or a function pointer, et cetera, or a lambda. And it just enqueues it into our queue. Pretty straightforward. So this is what using this thing looks like. We've got some atomic counter here that we're just using to have something to play with. We create a bounded depth task manager that has at most 64 tasks in its queue. We want it to have 6 threads in its task pool. And then we go submit 256 tasks to this thing. And each one of the tasks just increments this count by 1. But if you go and run this program, you might not see a count of 256 printed out here. Because at the end of this scope here, this bounded depth task manager gets destroyed. That destroys the thread group, which has a bunch of std_j threads in it. When those std_j threads get destroyed, they send a stop request to the underlying thread. And it's possible that one of those worker threads will see that stop request and exit before all of the queues are cleared. Or it's possible that all of them will see the stop request and exit before all the work has been processed. So we need, before those worker threads can actually exit, they need to make sure that the queues have been drained. So this is what we had before here. We just waited until we got a stop request, and then we stopped working. But that's not sufficient, because there might still be stuff in the queues when we get the stop request. So what we're going to do is we're going to add another loop after our main work loop here. And this loop is just going to, while we're just going to have a while true loop here. And then inside this loop, we're going to continuously try to dequeue things from the task queue. And as long as we keep succeeding, we're going to go and execute those things. And then once we're done, we're going to break here. So once we've drained the queue of tasks, then we know it's empty. And so we can go ahead and exit and be done. But there is still a bug here. A worker thread may block while dequeuing after all tasks have been completed, but before the stop request is received. So it's possible that that the queue is empty, but that there's a worker thread who is blocked in this tasks.dequeue, and there's no more work coming, so they're never going to wake up. And so we're going to have a deadlock. That worker thread is just going to always be waiting for more work that's not going to be coming. So what we need to do here is we need to control exactly when all the worker threads exit the first loop. And we're going to do that using another new C++20 synchronization primitive, a latch. So in the destructor of bounded depth task manager, which is where we're going to shut down the system, we're going to submit a special task to each one of the queues. We're not going to, or to each one of the worker threads. Now, we can't actually submit work to a specific worker thread, so we're just going to submit enough of these tasks for each one of the worker threads to execute one of them. And we know that none of these worker threads are going to execute more than one of these tasks, because we're going to have them wait inside of this task here. So first, we're going to create a stood latch, which is a single-shot barrier. So a certain number of threads can all arrive at this thing, and once they've all arrived, then they will all proceed with their computation. So this stood latch, we're going to wait for however many worker threads we have plus 1, because the current calling thread wants to participate in this barrier as well. So we've got a precondition that this destructor is not called from within one of the worker threads. That would be bad. This would blow up. So then, for each one of the worker threads, we will submit a task to the queue, and that task will just arrive and wait on the latch. So when each one of the worker threads dequeues this, it'll call that arrive and wait, and then it'll wait until everybody else has gotten there. And then, after this, we know that none of the threads have left that first loop yet, and so, or we know that none of the threads have left the first loop yet. Then we can send our stop request. And then after we've sent the stop request, we can release the barrier, the latch here. So what we're trying to do is we're trying to hold everybody right here until we've sent the stop request. And so once we've sent the stop request, then we can say to everybody, hey, we're going to release all of you by arriving on this barrier. And then at that point, everybody will come out of this call. They'll then exit this loop. They'll see, hey, it's been requested that we stop. So everybody will see the stop request. They'll then go into this loop here that'll process any outstanding tasks. And then everybody will terminate, and there will be no deadlock. Yeah. So let's talk a little bit more about latch. So this is what the latch API looks like. So when you construct a latch, you tell it how many things you want to participate in the latch. And you can just arrive on a latch. You can just decrement the count on the latch. You can wait on a latch. And you can arrive and wait on a latch. And you can arrive and wait with a count that's greater than 1. The same thing for countdown. You can arrive with a count greater than 1. All right. So now let's go and find another way to break our little queue. So we're going to create this submit tree task. And what this task is going to do, it's going to increment some atomic. That's sort of unimportant, this count atomic here that it takes as a parameter. But then it's going to also take this level parameter. And if its level is not 0, then it's going to go and spawn 2 children tasks, each with a level that is 1 less than the parent task, that is going to also go and call submit tree. So this will spawn a binary task tree. And so like we use it here. We do a submit tree with a level of 8. So this will go and spawn a whole bunch of work here. So the bug here is that this code is going to deadlock, because this is going to create a whole bunch of tasks, and each one of these tasks is going to try to submit more tasks to the queue. The problem is that eventually the queue is going to fill up, and then submit will block because it's waiting for space to become available. But all of the other worker threads are executing these submit tree tasks, and what these submit tree tasks are doing is they're trying to submit work and waiting for somebody else to come in and clear out space in the queue. So like in this example here, we've got 6 threads in our task manager. What's going to happen is eventually all 6 of those worker threads are going to be in a call to submit tree, calling submit, blocked, waiting for somebody to come and execute work from the queue, but nobody's going to do that. So what we need to do is what's called boost blocking. So when we want to block on some entity, we need to ensure that entity's we need to delegate the forward progress of our current thread of execution to that entity. We need to ensure that that entity will eventually unblock us, that is. So one way that we can do this is instead of just submitting instead of just enqueuing our task here with a blocking in queue inside of submit, we can call try and queue repeatedly which is a non-blocking mechanism. And then when try and queue fails, we can call this make progress function. And what this make progress function needs to do is it needs to ensure that space in the queue will be cleared up. Because the condition for try and queue to succeed, the condition for us to make progress, is that we need there to be space in the queue. So how can we ensure that there's space in the queue? Well, we can go execute items that are in the queue here. So this is a little bit weird, because now we've taken our submit method, and our submit method might actually go and dequeue things from the queue and run those things. But this will solve the problem that we had. It will ensure that our little submit tree example will make progress. Now, there is still a bug here, because we might blow out the worker thread stacks with recursion, because we'll end up with, on the stack, we'll have a call to submit tree that'll be calling submit, that will be calling submit tree, because it'll be right here dequeuing things, trying to make space for this submit call to succeed. And so then you'll have a bunch of these calls in the stack. But we're not going to worry about solving that bug. All right. So this is our bounded depth task manager. We've built our little mini runtime. So now let's look at what we can do with it. Let's build a couple little parallel algorithms. So let's start off by building a parallel histogram function. So this is first we'll look at what the serial implementation of histogram looks like. So histogram is going to take some input sequence, some output iterator. It's going to take a amount to increment each value by, and then it's going to take a mapping operator, which is going to take the value of each input element and index that value into the output sequence here. So the way that we implement this in serial, we just have this for each function. And the for each function, it just indexes into output using op, and then it increments it. So it's pretty straightforward. All right, now let's look at a parallel version of this. And for the parallel version, we're going to need to assume that the input and output iterators are random access, or that the ranges here are random access, and that and we also added a execution policy parameter right here. Let's just pretend for now that this is like a C++17 execution policy. All right, so here's the body of our parallel histogram function. So the first thing we want to do is we want to figure out, we're going to spawn off some number of tasks, each of which is going to handle a part of this problem. So we're going to go figure out how many elements are in the input. Then we will figure out how large we want each chunk of work to be. We're going to pretend that our execution policy has some magic chunk size function on it that tells us what's a good chunk size to use, what's a good granularity for the work. Then we need some way to synchronize all of these work items. So we're going to use a std latch for this. And then we're going to go and create a bunch of chunks. We're going to do that by submitting those chunks to the execution policy. So submit is just going to be some method on the execution policy that takes a task and executes it. Then inside of this submit function, we're going to go and compute the beginning and end of the chunk that we're currently executing. And then we're going to go call basically the serial version of the algorithm that we just saw a moment ago. We'll just go call it just locally on our chunk. So we just say for our chunk, just go and do the, compute the index for each one of the input elements, and then for that element in the output, go and apply the increment. Now, the problem here is that two different chunks might attempt to update the same element in the output at the same time. So what we need is we need our increments to output elements to happen atomically. We could use a mutex, but that might be slow. Or we could force our users to provide us with a sequence of std atomics as the output. But it would be a sort of unfortunate requirement if we said, hey, your output elements, they can't be just t's. They need to be std atomic of t's. Because this this parallel algorithm, the parallelism should be transparent to the person calling this algorithm. So in C++20, we have another feature which helps us out here. It's called atomic ref. An atomic ref is a facility that lets you temporarily view any type of object as an atomic object here. So you construct an atomic ref by giving it a pointer to some other object. And then, as long as everybody else who is concurrently accessing that object is also using atomic ref, you can treat it just as if that object was a stood atomic. So here we just declare a stood atomic ref to whichever element is the one that we want to increment. And then we do a fetch add on that element here. And here is our parallel histogram implementation. So let's talk a little bit more about stood atomic ref. So stood atomic holds a t. Stood atomic ref does not hold a t. It's a reference to a t. But otherwise, they have the same API. Another thing here, this algorithm currently, we're using fetch add, which means that this is going to only work if our output value type is an integer, because fetch add before C++20 only worked for the integer specialization of stood atomic. But in C++20, we've now added stood atomic floating point specializations. So now you can call all of the various math functions on atomics of floating points. So fetch add, fetch subtract, multiply, etc. All right, and then the final thing in our parallel histogram we call countdown on the latch, and then we block on the latch, but we don't block unconditionally. We call some make progress mechanism to ensure that we don't deadlock the system. And then in the calling thread, whoever launched this parallel histogram, we do the same thing. We wait for the latch to be ready, and we continuously call this progress mechanism until that happens. All right, now let's look at one more parallel algorithm, and then we'll be done. This one's a little bit more complicated. This is going to be a parallel implementation of exclusive scan. So exclusive scan is an algorithm that takes a range of values and writes the sum of the first n-1 elements into the nth element of the output. So each element of the output is the sum of all of the prior elements in the input. And so here, input is a range, output is an iterator, op is a binary function object. For example, it might be like stood plus. So this is somewhat similar to stood partial sum, except partial sum would include the element at the nth position. Exclusive scan does not. So let's look at a little example of this. So suppose we have some array of 9 elements here, A, B, C, D, E, F, G, up to I. And so the exclusive scan of this would look like this. So x here is some initial value. The initial value is significant because the first element has no prior elements to it. So the first output element is just the initial value. And then the second element is the sum of all the one element before it plus the initial value. The third element is the sum of the first 2 elements and the initial value. All right, so how do we go about parallelizing this algorithm? So we're going to look at an approach that only supports non-commutative and non-associative operations, but that's the usual restriction that we have when designing these sorts of parallel algorithms. So let's start off by taking an approach similar to what we did for histogram, where we're going to take our original problem, we're going to split it up into chunks. So we'll split this up into 3 chunks, and then on each one of the chunks, we'll start off by running the serial version of the algorithm, just stood exclusive scan in each one of these chunks. So for the first chunk here, we take ABC, we do an exclusive scan on that. That gives us some unspecified value in the first element, then A, and then A plus B. Same thing for all the other 3 chunks. Then we need to go and sort of figure out a correction that we need to apply to everybody. Because we've computed a local value here, but this problem requires global knowledge. We need to distribute like this AB sum here. That needs to be included in the results for these three here, and in the results for these three here. And this DE sum here needs to be included in these three elements as well. So what we're going to do is we're going to take the value of the last element of each one of these local scans. We're going to add it to the last element of the initial array. So basically, we're going to compute the sum of each one of the chunks. And we're going to stick the sum of each one of these chunks into some array we're going to call aggregates. And we'll do this for each one of the chunks. So for the first chunk here, we end up with a value in this aggregate array of ABC. And then in the second chunk, we get DEF. And then in the third chunk, we get GHI. Then we're going to run an exclusive scan on this aggregates array. We're going to do this in serial on one thread. And we're going to add in the initial value at this point. So what we'll end up with in this aggregates array is x, and then xabc, and then xabc def. Then, going back to parallel again, we're going to increment all the values in each one of these chunks by their corresponding entry in the aggregates array. So all of the elements in the first chunk will increment by aggregate 0, which is x. Second chunk will increment by x abc, etc. And then this gives us the output that we desired. So in the real world, there'd actually be a few more levels of hierarchy here. For example, if you were implementing this on an NVIDIA GPU. But it's simpler for us to just think about this in terms of these two levels here. We have a section of a first pass that's parallel. Then we do some aggregation calculations in serial. And then we go back to parallel to apply a correction to everybody. So traditionally, we call this first parallel pass an upsweep because the amount of parallelism is decreasing. And then we call the second pass a downsweep because the amount of parallelism is decreasing. In the upsweep here, we are taking information from everybody, and we're sending it to one guy. And then in the downsweep, we're taking the information that one guy computed, and we're sending it out back to everybody. All right. So unlike the histogram algorithm, we're going to implement this as a collective algorithm. So we're going to have this exclusive scanner struct. It's got the same parameters as the serial version. So it's got the input range, the output range, initial value, and some invocable. Those are just going to be member functions. Then we're going to have some constants that will compute in the constructor, the amount of concurrency, so how many concurrent actors are participating in this collective operation, the number of elements in total, and then the chunk size. Then we're going to have some this stud vector of aggregates that we'll use for the storage of the aggregates. And then we're going to have two synchronization primitives. One, a stud barrier that we're going to call upsweep barrier, and then yet another latch. So stud barrier is a heavier weight version of stud latch. So stud barrier can do two things that latch can't. You can arrive at a barrier multiple times. Barrier supports multiple phases of arrivals. Latch, you can just arrive, like there's just one phase. Like everybody arrives and then it fires off and then you can't use it again. Barrier, you can use it to synchronize multiple different phases. And barrier also supports a completion function. So a completion function is this function that gets run by one thread at the end of each barrier, at the end of each barrier phase. So the completion function, it takes on a construction in addition to taking the count of how many threads are participating in the barrier. And because there are multiple phases of a barrier, if you want to arrive at a barrier and then wait on it later, as you can with latch by calling countdown and then later calling wait, well, you need some sort of handle to the barrier to know which of the phases you're going to be waiting on later. And so instead of having a countdown method on barrier, we have this arrive method, and it gives you back an arrival token. And then if you want to wait on that arrival token, you give it back to the barrier when you go to wait upon it. We also have an arrive and wait, just like stood latch, and we have an arrive and drop, which is somewhat similar to stood latch's countdown. So arrive and drop is just like arrive, except it doesn't give you back an arrival token. This is useful because arrival tokens are no discard, because if you're asking for the arrival token, you need to do something with it. All right, so this is latch, which we looked at earlier. So the sort of comparing these two, both of them support asynchronous arrival. With barrier, it gives you back this arrival token. With latch, it doesn't need to. Latches are single phase, whereas barrier is multi-phase. Latches don't have any notion of thread identity. So a thread may arrive multiple times on a latch, and any thread may wait on a latch, even a thread that didn't participate in that latch. And latches don't have a completion function. Now, barrier does have a notion of thread identity. A thread may only arrive once per phase, and only a thread who arrives may wait. You can't transport arrival tokens between threads. And also, barrier supports completion functions, and that's the reason that we're using it right here. So we're going to use a completion function with barrier here. We're just going to use stood function in this case. And the thing that we're going to have this completion function do is it's going to do that serial phase in the exclusive scan algorithm. It's going to scan up this array of aggregates. So we've got a couple functions here. We'll walk through them. So that's the constructor. It's pretty boring. We just initialize the various counts. We compute the chunk sizes. We construct the barrier, et cetera. And then we have this scan aggregates function, which is actually pretty boring. All it does is it does an exclusive scan on this aggregates array. And it adds in the initial value at this point, as we discussed earlier. So now let's look at this launch member of exclusive scanner. So launch takes one of these execution policy things, and it's going to create a bunch of tasks in some loop, as we've seen before. So the first thing it's going to do is it's going to go and compute what's the range that I'm working with here, and then it's going to call this process chunk function on that range. And then again, we're using a latch here, the downsweep latch, to synchronize with all of the chunks that we've spawned. So the real meat of this is in process chunk here. So inside of process chunk, we get the index of the chunk that we're on, the range of input we're working with, and the range of output that we're working with. And so the first thing we're going to do is the upsweep. So in the upsweep, first we do an exclusive scan of the input elements, and then we wanted to get the sum of our chunk. And so the last element of the exclusive scan is the sum of all of the elements of our chunk except the last element, because it's the sum of all of the elements prior to the last element. So we just take the result of the last element of the scan, and we add it to the last element of the input. And that's the value that we put into the aggregates array for our chunk. We don't have to do anything to protect access to the aggregates array, because there's one entry in the aggregates array for each one of the chunks, so everybody can write to it independently. Then once we've completed the work for our chunk for the upsweep, we go and arrive and wait at the upsweep barrier. And after the last person arrives and waits at this barrier, then the completion function will run. So the synchronization semantics of stood barrier is you have n people arrive, then you have the completion function, which happens after those people arrive, and then the waits complete only after the completion function has run. So you've got memory barriers on both ends of this. So before when we start executing the completion function, which scans the aggregates, we know at that point that all of the threads have computed their aggregate, and they've written it into their chunk, into their slot in the aggregates array. And we know that we can see that value. And after we've completed the weight on this upsweep barrier, we know that the serial scan of the aggregates has been completed and that we can see the results of that. And so then we can go and we can apply the correction to each one of the elements of our chunk in the downsweep pass here. We just use stood for each, and for just each element of the output, we just add in the aggregates value for our chunk. And then the final thing we do is we arrive at the downsweep latch to signal to the guy that launched us that we're done. And this is a sort of naive implementation of a work-efficient exclusive scan. The actual best way to implement an exclusive scan on a GPU is a slightly different algorithm, but that doesn't fit as nicely on a slide. All right, so what did we talk about today? We talked about various enhancements to stood atomic, the wait notify interface, stood atomic ref, the test interface for stood atomic flag, floating point specializations. We talked about stood latch and stood barrier, two new types for coordinating groups of threads in C++20, counting semaphore, which is a lower level, more general form of a mutex, and stood jthread, a enhanced thread class that has a joining destructor and that supports this interruption mechanism. All right, and that's my talk.